principal stresses. Here's a surprising and amazing fact. For any stress tensor, there's a coordinate system where that stress shows up as only normal stresses. Okay, so you can make up any stress tensor, just make up numbers as long as it's symmetric. Somewhere there's a coordinate system where if you use the rotation matrix to transform that stress tensor into this new view, if you think of the coordinate system as just a way of viewing or a way of measuring it, where that same state of stress shows up as only XX, YY, and ZZ elements, no shears, okay? For like a material, that means, load some body. Okay, so if I press down on this, I'm creating stresses over here by the hinges, and we could measure those stresses and we get some shears and some normals. And then we could convert it to a coordinate system where if we had taken those measurements in that coordinate system to start with, all we would have is normal stresses. It's a little surprising because you kind of have this feeling that shear stresses and normal stresses are fundamentally different things. A shear stress, I mean, the name of shear stress is because you sort of create those stresses by doing what scissors do to a material. You push down on one side and push up on the other side. But it turns out that the fact that it's a shear stress really is just has to do with what your coordinate system is. Okay. Okay, well, you have to give me that. It's pretty surprising. But whether it's useful is not clear yet. But there's another surprising and amazing fact. In that principal coordinate system, one normal stress is the maximum you can find anywhere, the maximum you can find with any coordinate system. And another one is the minimum you can find with any coordinate system. Another normal stress is the minimum that you can find with any coordinate system. Okay, well, that sounds a lot, makes it sound a lot more believable that this is something useful. Because for any state of stress, like you're doing something to a big lump of metal or something, your coordinate system tends to be just based on like what's easy for you to measure. So how do you compare a stress tensor in this random coordinate system to another stress tensor over there? Is there any way to quantitatively measure which one is a bigger stress or more likely to damage this material? Well, if you can find this coordinate system where everything is represented by these principal stress tensors, then you can say, okay, this maximum is bigger than this maximum, and this minimum is smaller than this minimum. It gives you a way to compare these matrices of values, okay? So are you with me on that? That seems like a useful tool for, and then there's one more, this is the last one. Another surprising, amazing fact. Once you find those principal stresses, it's easy to calculate the maximum shear stresses that you could find with any coordinate system. Um, and so once you know the maximum and minimum normal stresses, and the maximum shear stress, you can determine the likelihood of failure, of this thing reaching whatever failure criterion you're concerned about. Okay, so that's why we want to calculate these principal stresses. So you're given any old state of loading, you're given all the stress elements in some random coordinate system, and you want to find the coordinate system where that loading can be represented with only normal stresses. So first of all, that gives you the maximum normal stress that you could find if you rotated that coordinate system all around. You'd look at all the normal stresses at all the coordinate systems. This principal one has the maximum and the minimum. And when I say minimum, I don't mean minimum absolute value. I mean maximum compression if it's in compression. So you can think of this as like maximum tension and maximum compression. And then with a easy calculation from there, you can calculate the maximum shear stress value that you could have with any choice of coordinate system. And using those values, you can say with some confidence whether you're concerned about this steel thing that's built into the door or whatever being damaged by the loads. Okay, that's the idea here. Okay, so how are we going to find the principal stresses? And calculating the principal stresses is an eigenvalue eigenvector problem. And the basic idea of an eigenvalue eigenvector problem is you have some matrix and you multiply it by some unit vector. Multiplying it by that matrix gives you a vector that is parallel to that original unit vector, and the magnitude is changed by some factor lambda. Okay, so that's the definition of an eigenvalue eigenvector problem. And these are going to come up in all your classes basically starting now. Okay. So what's special about this equation? And I haven't talked yet about how this relates to what we want to do, but it comes up in a surprising number of calculations that are important in engineering. What's different about this problem than any other matrix calculation? Like in general, if you multiply a 3x3 matrix times a 3-element vector, okay, you're always going to get a vector back. But in general, that vector is going to be not just have its magnitude changed, but it's going to be rotated in some way. Okay, like try it with, like, doesn't that always work? No. For example, let's take this matrix 1, 3, 6, 0, 2. Let's even make it symmetric because we're going to be dealing with a symmetric matrix 6, 1, 0. Okay, and multiply it by the vector 0, 1, 0, just to make it easy to visualize. The matrix you get out is 3, 2, 1, which is clearly not in the same direction as 0, 1, 0. Okay, but in this eigenvalue equation, this is the same direction as n. Okay, so that's what we're looking for. We're looking for special cases where multiplying the matrix by a unit vector gives you a new vector that's in the same direction. All right, so I guess before I go into the calculation, let me derive how this comes about in our problem. Okay, so this is the derivation of the eigen problem for principal stress. So let's start with this stress tensor. I'm going to call it sigma xx, xy, xz. I'm going to take advantage of the symmetry. And now we're going to use the idea that if you multiply the stress tensor by a unit normal vector, a unit vector, it gives you the tractions on the face that it's normal to, right? So if we're looking for a face that only has normal stresses, and we multiply this by, this outward facing unit normal, what would it mean for that face to only have normal stresses on it, only have normal traction component on it? Can you picture that? So basically, you can think of this unit vector as the outward facing normal for whatever unit vector you give. That's the outward facing normal vector to some face. So if this is your face, this is your outward facing normal. Well, if that face only if that doesn't have any shear components to the traction vector, then it's going to be just parallel to that vector. It could be in or it could be out, depending on what the factor is that you're multiplying it by. The normal goes that way. The traction can go either way. I'll draw it the other way just so you. Okay. And so we can write this as lambda times this same unit normal. And so the idea is that we're trying to find a face where the outward unit normal and the traction vector are in the same direction. So now, how do we solve that? How do we come up with? So what we're trying to do is we want to find. We need to find two things. We need to find the outward unit normal. That's n hat. And that's what's going to be called the eigenvector. And we need to calculate the lambda, that constant of proportionality, and that's called the eigenvalue. And that's the principal stress value. This equation, we have it up here. Okay. And I'm going to rewrite that as, so write out these elements again. And multiply it by the outward unit normal again, nx, ny, and z. But now I'm going to rewrite the right side. So notice that I can rewrite this as a lambda times a matrix with ones on the main diagonal and zeros everywhere else. times that same unit vector. Okay, this is called the identity matrix. Why would you call that the identity matrix? Like what happens to any vector you multiply to this matrix? It gives you back the same vector. So putting this in here gives us exactly the same value as if it wasn't here at all. Okay. But now that I've done that, well, let me rewrite this again one time. So now I'm going to carry that lambda through this identity matrix, and we have just lambdas on the main diagonal. Okay. And now I can subtract this from both sides. Because each of these two matrices is multiplied by the same vector. Okay, so now I'm going to rewrite this like this. Sigma xx minus lambda, sigma xy, sigma xz, sigma xy, sigma yy minus lambda, sigma yz, sigma xz, sigma yz, and then sigma vz minus lambda times that unit vector is equal to 0. Okay. There's two types of solutions to this. The first one is the trivial solution. And that is just so let's see. That is that nx equals ny equals nz equals 0. Okay, that one's useless to us, so we don't care about that one. We want to make sure that we're not getting that one. The one we want comes when this matrix is not invertible. So we're going to require that left matrix is not invertible. And we're going to do that by finding where the determinant of that matrix is 0. So set the determinant equal to 0. And that's where we'll stop right now. So we have this equation with this matrix, just a matrix of numbers, and it's still symmetric because all we've changed are the diagonal elements. And we're going to set the determinant equal to 0. That's going to give us 3 different answers for lambda and 3 different corresponding answers for that unit vector. And those are going to be the coordinate system directions for our principal coordinate system. We're looking for the inclined faces, looking for faces. And, these are not, like, generally speaking, these are not the faces of the stress cube. These are at some kind of weird angle. We're looking for the faces where the traction vector is parallel to the outward facing normal. Outward facing unit normal. So that's what we always call n hat. And when we find these, what we've found, so these are faces with only normal traction components. Okay, so what we ended with last time was we had this equation that said, we derived that this is what we need. We need to satisfy this equation where sigma xx minus lambda, and then sigma xy, sigma xz, sigma xy, and then the quantity sigma yy minus lambda, and then sigma yz, sigma xz, sigma yz, and then finally sigma zz minus lambda. Times this unit normal, this unit vector, nx, ny, nz, is equal to zeros. And to get a non-trivial answer, we have to set the determinant of that matrix equal to 0. So the determinant of, I guess I'm going to write it again. Looks like I am. Sigma xx minus lambda, sigma xy, sigma xz, sigma xy, quantity sigma xx minus lambda, sigma yz, sigma xz, sigma yz, and the quantity sigma zz minus lambda. Determinant of that matrix is equal to 0. Yes? Yes, it should. Thank you. Okay. So the way you calculate the determinant of this matrix is, you can go a couple of different ways, but I'm going to go, so it's going to be this times the determinant of this little 2 by 2 matrix minus this times the determinant of cross out this and the determinant of that little matrix, plus this times the determinant of this little matrix. I'll just give you the formula, but what? It's like how you do the cross product, yeah. This is sigma xx minus lambda times the quantity sigma yy minus lambda times sigma zz minus lambda minus sigma yz squared minus the quantity sigma yy minus lambda times the quantity sigma xy times sigma z minus lambda minus sigma xz sigma yz and then plus, this is all one line, sigma xz times the quantity sigma xy sigma yz minus sigma xz times the quantity sigma yy minus lambda, and set that equal to 0. Yes? The second one is supposed to be yes. Thank you. Minus sigma xy times, and that other stuff looks right, and then, yeah. Okay, so what does it mean to find the roots of this equation? So all the sigmas are given. So we're looking for lambda values. This is a cubic polynomial. So there are 3 roots. And for each of those roots, there is a corresponding unit vector n. Okay. So that's the idea. The roots are, these are called the eigenvalues, those lambdas. And in this application, those are the principal stresses. These unit vectors are called the eigenvectors. They're mutually orthogonal. So they're all perpendicular to each other. And together, they tell you the coordinate system where this thing happens that we're looking for. So together, those 3 give a coordinate system with only normal stresses. So in practice, how do you find these? Well, on a TI 89 or Inspire, you use the command EIG, those are all lowercase, and then capital V lowercase l of the matrix. Okay, this is the original stress tensor. And it gives you a set of values, sigma 1, sigma 2, sigma 3. And then if you use the command EIGVC of that matrix, it gives you a matrix that's like N1x, N2x, no, that's exactly wrong. N1x, N1y, N1z. That's the first eigenvector that corresponds to this one. Then N2x, N2y, N2z. That corresponds to sigma 2. And N3x, N3y, N3z. And that corresponds to, so these two correspond, these two correspond, and these two correspond. The lambda? Yes, and so if you make a coordinate system out of, so if you use plus or minus N1, plus or minus N2, and plus or minus N3 as coordinate system axes. Okay, so this is your new x-axis, y-axis, and z-axis. Okay, and the plus and minus are just to make sure that it's a right-handed coordinate system, because you have to have a certain relationship between x and y and z and x, right? X cross y has to be equal to z, y cross z has to be equal to x, x cross z has to be equal to negative y. Then the new stress tensor is sigma 1, sigma 2, sigma 3 with zeros everywhere else. Cool, right? Now, if we call, let's say sigma max is the maximum of those three. Sigma min is the min of those three. And sigma mid is the third one, whichever one isn't a max or a min. Okay. Now identify the axis corresponding to sigma mid. Okay, so each of, this is 20, this is 5, this is 8, say, okay? So 20 is the max, 5 is the min, and that means the middle one is the z axis, okay? Then if you rotate your coordinate, so now rotate the coordinate system plus or minus 45 degrees about that middle axis. It'll give you a stress tensor with the maximum absolute value of shear stress. And absolute value, tau max, is going to be equal to sigma max minus sigma min divided by 2. So if you need the whole stress tensor, you can do it with that matrix transformation. If you only need the value, you can just use that simple formula. And knowing what that maximum shear stress is a really important thing for determining when something is going to, reach different stress limits associated with breaking, So now here's the problem. Here's the example problem. So for this stress tensor, 8.83, 0, 3.21, 0, negative 5, 0, 3.21, 0, 1.698 megapascals. We want to find sigma max, sigma min, and max shear. Okay, so we need to find the determinant of, or we need to find the lambda values where 8.83 minus lambda, 0, 3.21, 0, negative 5 minus lambda, 0, 3.21, 0, 1.698 minus lambda, 1.1698, okay? Well, let's round that to 1.17. And we're going to set that determinant equal to 0. So this gives us the polynomial 8.83 minus lambda times negative 5 minus lambda times 1.17 minus lambda minus 0 plus 3.21 times 0 minus 3.21 times negative 5 minus lambda, and all this is equal to 0. So this is 8.83 minus lambda times, I'm going to FOIL out the inside, so what's negative 5 times 1.17? $5.85, and then plus 5 lambda minus 1.17 lambda plus lambda squared, and then what's 3.21 squared? Okay, so negative 10.304 times negative 5 minus lambda, and this is all equal to 0. Let's simplify a little, so we have 8.83 minus lambda times the quantity, negative 5.85 plus 3.87 lambda plus lambda squared. I guess plus 10.304 times negative 5, or 10.304 times 5. 51.5. Am I losing you? $51.52, and then plus 10.304 lambda, and that's equal to 0. We're so close to having, so all we have to do, our last painful thing we have to do is FOIL out this, distribute this first thing. We're gonna, so it's okay if we get a cubic as long as there's no constant term, because then you can factor out, one of the answers is going to be 0. So what's 8.83 times negative 5.85? 0.65? The 5 is continuous? Okay. And what's 8.83 times 3.87? 34.17 lambda plus 8.83 lambda squared, and then plus 5.85 lambda minus 3.87 lambda squared minus lambda cubed plus 51.52 plus 10.304 lambda is equal to 0. And you can see that those cancel if you're a naturally sloppy person. Okay, so what do we get? That's what we needed, those to cancel. So we have, there's our cubic. Our squares are here. Our linear terms are here. And so we get negative lambda cubed. What's 8.83 minus 3.87? So plus 4.96 lambda squared. And then what's 34.17 plus 5.85 plus 10.304? 50.324 lambda is equal to 0. If I pull out I'll pull out one negative lambda, and we get lambda squared plus 4.96 lambda plus 50.324 is equal to 0. One of our roots is 0. The other one we can get with what? Yes. These are both minus, right? Yeah, you never have to do this, right? But I just want you to, and it's not this step that I want you to see, it's the next step that I want you to see, coming up with the eigenvectors. But I think this is one of those things that's useful to do once and then never do again. Okay, so can someone give me the roots? Okay, so 0, negative 5.035, okay, and then so this is our negative 5 that we started with. This is our 10 that we started with. We didn't get it exact because everything's rounded, you know. Okay. So now, how do you come up with the eigenvectors? Usually, by the way, in practice, these are all that matter to us. But if to get the eigenvectors, that tells you the orientation of this principal coordinate system. And so like it could be useful. It just usually you're not looking for those. But now we want to find the eigenvectors. And so what we're going to do is one by one, plug the roots for lambda into the eigenvalue equation and solve for this unit vector n. Okay. So first, let's do it for the let's do it for lambda equals 0. So we're going to plug that into our eigenvalue equation. Well, the eigenvalue equation, if we go back to the original problem, says so we're going to plug the 0 in for lambda, okay? And we're going to have this matrix times that unit vector is equal to the 0 vector. And we're going to solve for those n's. So okay, so I'm taking this. And what we're going to solve is this, with 0 in place of all these lambdas. Okay, so and so the first equation, if you do the matrix multiplication, you get 8.83 nx plus 3.21 nz is equal to 0. Okay. The second equation, you get that negative 5 ny is equal to 0. And the third equation, you get 3.21 nx plus 1.17 nz is equal to 0. Okay. So what does this tell us? So let's say that for now, let's choose nx equals 1. Okay. What does that tell us about nz? So we have 8.83 times 1 plus 3.21 nz is equal to 0. So nz is equal to negative, what's 8.83 divided by 3.21? Let me guess, 0.940. No, 0.342. Oh no, it's not going to be that yet. We're going to have to 8.83 divided by negative 3.21. 2.75. Okay, so we have this vector now that says, so our n is equal to 1, 0, negative 2.75. But it's not a unit vector. Okay, so now normalize it. And you get, divide everything by 1 squared plus 2.75 squared square root. And I hope what we're going to get is 0.3420, negative 0.940. Okay, so that says that the coordinate axis, the axis of the new coordinate system, corresponding to the principal stress of 0 is plus or minus, it can be either direction, 0.3420, negative 0.940. Yeah, so there's always redundancy in this system. Uh, these two are always going to be, there's always going to be two that are linear multiples of each other. So just two, like you can just choose some arbitrary value and then normalize it at the end. It looks like we have 3 equations for 3 unknowns, but it's really only two independent equations for 3 unknowns. Okay. All right, so that's the first one, and you can see, like, why did I know these were going to be 0.342 and negative 0.94? Because at the start of this, the way I got our coordinate system was I started with a principal coordinate system and then did a 20-degree rotation. And so what we have here, cosine and sine of 20 degrees. Okay. And when we do so I'll finish this on Wednesday. I think there are problems you should be able to do before I finish this. But we're going to do it now for the 2 other eigenvalues. And what we're going to get are unit vectors that are perpendicular to that one. And so we'll have 3 vectors that are all perpendicular to each other. We can make a coordinate system out of them. And they're all rotated 20 degrees about the y-axis from our original.
And then we get the values that we want in the first place.
Yeah, so we already got the values when we calculated those eigenvalues. That's the step you have to do first. And then from those, this is the 0, negative 5, and 10. And then from those, you can decide which one you want to represent your x, your y, and your z. You can choose any order you want. So if, like, as soon as we got this, you could just say, okay, my principal stress tensor is 0, negative 5, 10 along the diagonal, and that's the end of it. All the rest of it is just to figure out the orientation of that new coordinate system relative to the old coordinate system.